A lot different than 5G. So today we're going to start in the labs at Northeastern University. We'll see what they've been working on, including a 130 gigahertz MIMO system, a 6G networking test setup, and what it takes to turn MATLAB programs into actual RF communication signals. We'll also dig into the possible applications of this research for 6G. We'll then come back here where I'll be joined by 6G expert Roger Nichols to discuss the current and future state of 6G. First up, let's jump over to the Ultra Broadband Nano Networking Laboratory at Northeastern University in Boston to talk with the lab director and professor, Giuseppe Jornet, about how he got started and what's going on now in sub-terahertz research. I asked him, what is sub-terahertz and when did you first start working on it?
In 2009, 2010, when we started working on terahertz, at that time I was a PhD student, people were not even working at 60 gigahertz. People were still fighting, trying to see if that could work, right? So anything beyond 60 gigahertz was already terahertz. So in our first papers, we used to say 100 gigahertz and up, it's terahertz. Now what has happened? In the last 5-6 years, especially as millimeter wave has become more prominent, the 60 gigahertz band supposed to be working, this and that, people say, hey, 100 from 100 gigahertz till 300 gigahertz, it's still millimeter wave. But the name millimeter wave has been abused, so, let's call that sub-terahertz. So as of today, people will agree sub-terahertz is 100 gigahertz till 300 gigahertz, and then from 300 gigahertz up to 3 terahertz or even 10 terahertz, that's the terahertz band.
This is like log scale thinking at its finest. Anything above 100 gigahertz is
absolutely, because
band.
If you think as of today, all the wireless services that we're using, think of your cell phone, your Wi-Fi, your TV, your radio, your GPS, all the sensors in your car, all the radars, they are all under 100 gigahertz. So we could take all those and put them again between 100 and 200 or 200 and 300. No, we're talking logarithmically, as you said. We're saying, no, we can take that, but now multiply it by 10, right? We can go from 100 to 1 terahertz or 1 terahertz to 10 terahertz. That's what gets exciting.
So I have to imagine it's more complicated than just slapping up converters on everything. Can you talk me through some of the technical complexities? Because what you're doing in the lab is absolutely incredible here. What does it take to go from 60 gigahertz to terahertz or 600 gigahertz?
Absolutely, very good point. And I would like to highlight 2 things. First, we are not just going to higher frequencies so we can be at higher frequencies. We go to higher frequencies because we are promised that we will find larger bandwidths. So I would say there are mostly 3 things that are challenging to get to those frequencies. First, indeed, you need to be able to push your center frequency towards the sub-terahertz and terahertz band. And sure, there are ways to do that with frequency multipliers, and that's many of the things that people used to do. There are other devices that actually intrinsically work at those frequencies. Those are not yet commercially available, but if you are bored and want to look at some of our patents, you'll actually see that we conceive devices that you power a DC battery and suddenly you have a terahertz signal without frequency conversion. That's something that exists and it's interesting. But that's just one of the parts, right? You could take a very narrow band system and push it up in frequency, but why would you do that? You want to go up in frequency and then have very, I would say, fat signals, broadband signals. So that's the second problem, which is how do you generate very broadband signals, signals that themselves have gigahertz of bandwidth. Like today in Wi-Fi, you are at 2.4 gigahertz with maybe with 100 to 100 megahertz and you're happy. No, I want to be at tens or hundreds of gigahertz and around that have my tens of gigahertz of bandwidth. So that's the other thing. And the problem that comes from these 2 is that you're trying to go up in frequency, and the result is that through all these multiplication processes, if you use multipliers, or even if you use the direct generation devices, your power is low. In addition, you're dealing with large signals, so you're spreading your power thin across all the bandwidth. Bottom line, the receiver suffers a lot. So what do you need? Well, then you need to make power from wherever you can. So if you cannot increase the transmission power, let's try to reduce the noise, but also let's help with antennas, directional antennas. Try to point the signal, so make sure that that little power you have goes only in the direction that you care. When we teach communication systems, we talk that you care about not just how strong is your signal, but how much stronger your signal is compared to the noise. And that noise that we always call, we don't put the adjective, but that's an amplitude noise, right? So we usually, when we talk about noise, we mean that your signal, the receiver, will have random fluctuations in amplitude. That's what we're used to do. That happens in all the systems. When you get to these very high frequencies, what happens is that not only your amplitude randomly fluctuates, your frequency itself may randomly fluctuate. So then it's why we start using the term phase noise. So we have phase noise on top of the amplitude noise, okay? And that's when systems get exciting. The reality is the following. Amplitude means that your signal goes up and down. When we talk about phase noise, if you imagine the constellation of your signal, and in some of these demos you're seeing constellations, what phase noise does is that it flips your constellation. It makes it, even if you have crazy phase noise, your constellation will start spinning. So good luck finding the symbols.
Right.
Okay? Amplitude noise takes them all over the place. Phase noise makes them spin. So that's the problem. This is something that at millimeter wave also happened before, but then people got better oscillators. When we get to the frequencies we are dealing, well, it depends. If you can, if you can get one of your good Keysight models, then your phase noise is going to be very low. But then when you try to make that into something cheap enough that you can put in every cell phone, you're going to experience phase noise.
I don't want to lug around a signal generator in my pocket, that's for sure. Yeah.
That's one of the problems. But again, for all the research that you're seeing here today in the lab, we're mostly dealing with professional grade equipment that gives us the ideal world to some extent. No, we can control how much power we have. We can control how stable our signals are. We can design the signals from scratch. As I always tell people, with the platform that we have many platforms, but with the one that we have been using the most, which is one of your arbitrary waveform generators and digital storage oscilloscope, anything we can conceive in MATLAB or mathematically, we can get it over the air. And we can get it over the air in a couple of hours. That's what we have telling collaborators, that's what we have telling to everyone that has asked me, Josep, we would like to build a test bed like yours. Sure, I'm an academic, I'm supposed to help you do that, and that's what we do. Of course, then you get to other platforms like your USPA platform that it's a little bit more challenging, but you only go there when you know exactly what you want to do, right? But right now in the lab, we have the opportunity to be able to, anything that we can imagine, as long as it does not break the laws of physics, we can probably test it.
So what I hear you saying is if you want to rapidly test different types of signals, this type of setup is really useful. And then you go to the USPA when you're ready to code some FPGAs and do it in real time, but a little less flexible.
So what I would say is the following. I'm sure that you have heard about the term the terahertz technology gap, right? And that's what has prevented the community for many years to use these frequencies. We just didn't have the technology. Technology meant many things. It meant having those signal generators that can go up to hundreds of gigahertz or a few terahertz. It also meant being able to process this very large bandwidth, right? And in the last, I would say 10 years, there has been a lot of progress. That has led to a lot of platforms. There are many publications that talk about a new modulator, right? And they show you a new modulator that only does modulation. There are people, for example, who do a lot of channel sounding, and that's perfectly fine. But in channel sounding, you know exactly what you're sending, so you just look for it and then understand what happened to it, that's the channel. With the platforms that we have here, what we are doing is, well, we can do anything you want. If you have a new modulation, we can try it. If you want to do channel sounding, we can do it. But if you have a new modulation, some error control, new synchronization strategy, all those things, as long as you can program them in MATLAB or Python or your favorite language, we can test them. The other motivation to then go to the real-time platform is that with what we're doing now, if the other is a real-time platform, it's because this is not a real-time platform. So I engineer my signals, I click play, they go out, I record them, and then I take my time processing them. And again, think for a second, we're trying to send signals easily at 100 gigabits per second. The goal is to get to 1 terabit per second. Go find me a processor that can swallow 1 terabit per second of data in real time.
Right.
So that's the challenge, right? So going to real time, it means, well, it's not just a matter of sending data, it's using the data. And when do you need that? Well, you need that if you don't want just to test one link, but if you want to test a protocol. I want you to send something very fast, I want you to confirm that you get it right, and I want this back and forth. So I need a platform that can think in real time. That's your USPA. Maybe I can tell this a little bit as the story of what was the research in my group, right? So first of all, 2009, I started my PhD. With my advisor, we eventually end up working on terahertz, and that's a very long story by itself. So we end up working on terahertz. And well, at that time, there was no technology, and people will say, why are you wasting your time? There is no technology. Fine. They said, no, there are people developing technology. Oh yeah, but the channel is horrible. Why are you wasting your time if the channel is horrible? Okay, well, we studied the channel. Well, it's not that horrible. If you understand it, you can design around it or even leverage what's unique of this channel. Oh, that's fine, but what type of signals are you going to send, right? There is nothing you can do. Said, well, no, at the very least, I can send the same type of signals, and that's what everyone does first. Then you say, no, but because of what I know from the technology, what I know from the channel, and what I've experienced with the typical signals, I know that I can do better by trying this, this, and this. Then the next question is okay, you can make one link, but good luck making a network. If everyone is directional and everyone talks so fast, just think, right? If you talk at 1 terabit per second or 100 gigabits per second, in a second, you send 100 bits. So you blink for a second, you lose 100 bits, 100 gigabits. It's okay. That's the problem, right? So you cannot blink. So that means that you need to start thinking how you design networks in a different way, right? And that's, I would say, where the field is now. There are a lot of publications and a lot of progress when it comes to the technology. There are more and more results showing how the channel looks like. I would say that there are more groups building communication solutions like what we have been building here, but only very few groups have really tried to build networks out of it. Not just a point-to-point link, but an actual network. That's what I think is going to happen next. Of course, there is a parallel process in all this, which is like, it's great to develop a technology, but if you cannot legally use it, what's the point? Yep. So one of the things that we also try to do here in the lab, it's contribute both to spectrum policy. So we send contributions to the FCC. You may remember in 2019, the FCC Spectrum Horizons was approved. So in 2018, we did send our inputs because the first time that I tried to get an experimental license, the answer was no. I was like, what? I'm an academic just trying something here. I was in Buffalo at the time. I say, yeah, no, but the frequencies you're trying to use are being used by, some very sensitive service, so you cannot. So, well, we had the help from people who knew more at the time, and we managed to get the license. But I think that things have gotten much better. Today, it's much easier to get experimental licenses at these frequencies. We also contribute to standardization. That's another thing that, again, why do we do that? Look, we can come up with very good solutions, but if no one uses them, what's the point, right? So as a university, we also try to do that. And for example, some of the students, like Divo later will show you some of his demos, or has already shown you some of her demos. Some of the solutions you've seen are actually part of the first terahertz standard that already exists. There is a standard for terahertz. It's the IEEE 802.15 3D. And it was approved in 2017. Now it has gone up for review, and in that there are some of the solutions from our lab part of the standard. So that's the technical part and the not technical part. Oh. And I don't know which one is more challenging, but okay.
Yeah. So Giuseppe gave us a great overview of what it takes to turn a 6G theory, a math equation, into a real signal that can be generated, modulated, and tested. But now we get to see it in action. This is a MIMO setup, meaning the one communication link has multiple input antennas and multiple output antennas.
So this is a MIMO system. So we have 2 transmitters and 2 receivers. They're working together to try to increase our data rate. So in this case, we're sending 2 separate data streams, one on each transmitter, and each receiver is receiving and demodulating those streams. We're operating at 130 gigahertz, which is a lot higher than any other MIMO system you've probably seen. And we're using 10 gigahertz of bandwidth. And this, right now, we're hitting about 36 gigabits per second.
So 36 gigabits per second over the air is insanely fast. It's one data stream going in and one data stream coming up, but it gets split up. Can you kind of walk me through, start to finish, what that signal chain and data chain, I guess, looks like?
Yeah, so we start with a bit stream, so just your zeros and ones, and we split it in half. And then those zeros and ones get converted into an IQ constellation. In this case, we're using a 16-QAM constellation. Those 2 sets of IQ streams get modulated to an intermediate frequency. In this case, we're using 5 gigahertz. That intermediate frequency signal is what we have generated in MATLAB, and it's getting passed to the arbitrary waveform generator. That is essentially our digital to analog converter. It'll create the analog signals that get passed to our RF front ends, which are also getting given an LO signal, which is at 130 gigahertz, and so that gets us to our carrier frequency. It goes through the air, and at the receiver, it's essentially the reverse process. So we have an LO coming in again at 130 gigahertz. It brings our signals back down to that same IF, and then we get to see them on our beautiful scope. They get digitized, and then in MATLAB, we're able to do the post-processing again, where we go to our IQ symbols and then our bits again.
So what's been the most surprising thing to you working with the system, getting it up and running and actually seeing it go from math and MATLAB into like a real system? Any surprises or anything along the way that you're excited about?
There are definitely challenges, but I think the most, I wouldn't say it's surprising, but it's exciting when it gets to working. With especially these heavy antennas, sometimes things move even if they don't look like they're moving, or someone knocks it, and then, with these antennas, they're very directional. So the beam width of these antennas is 1.6 degrees. So especially when we're this close, it's really hard to keep them aligned, and so that's one thing that can go wrong. Another thing that, especially for a MIMO system, in this case it's not as important since we have 2 completely separate streams that aren't overlapping. But if we are trying to do MIMO with more like a combining, or we're doing some pre-coding, generally the assumption is that you're transmit antennas, your receive antennas are the same. But in reality, we have two like separate hardware systems that are similar. They're made, like they were designed for the same like range of frequencies, but in reality they have different frequency responses. They behave differently, and so that can also cause some issues. Those are the two main ones that you don't really think of normally. But on top of that, there are also the main research challenges, of course, right? So we're working with a lot of bandwidth, and so with a MIMO system, generally you make narrow band assumptions, or you go to a multi-carrier scheme where you can use that narrow band assumption. At terahertz, if we go to a multi-carrier scheme, we generally have a high peak to average power ratio. So that means we have to transmit at a lower power if we don't want to damage our hardware. And when we already have low power, that doesn't go so well. On top of that, you have a wide bandwidth, you're going to eat a lot of noise, right? Because noise comes like, it's white. So as you increase the frequencies you're looking at, you get more noise. So larger bandwidth, more noise, less power, like there are those challenges as well that anyone working at these frequencies would see also. Generally, people have been doing single carrier, but single carrier it's tough to equalize in the frequency domain sometimes, which is what you need, especially if you're going with a wide bandwidth. We have very frequency selective hardware. So even though this is a line of sight channel, so we don't get multipath that makes our channel frequency selective, the hardware is making our channel frequency selective. So we need to account for that somehow. So we want the frequency kind of adaptability of something like OFDM, but we don't want the PAPR of OFDM, we want the PAPR of single carrier. So then we end up kind of trying to find something new, and I think in 5G people have also adopted doing DFT spread OFDM, which gives you kind of the best of both worlds. And so we have a MIMO system where we've shown DFT spread OFDM doing space-time coding over a broad bandwidth, and that's able to give us kind of the best of both worlds. So that's kind of where the engineering comes in, of we have these problems, we have solutions that maybe work for specific things, and we're trying to find a way to kind of put things together that makes sense. So I can try to realign these and make it look nicer if you want to get
let's
that.
try and realign it. Yeah.
So this is our 16 prim. We have the two streams.
Yep.
One's purple, one's orange.
Yeah, I mean, look at this bit error rate. That's pretty zero.
0%.
And then
Like to
32
see that.
gigabits per second. This was my first time inside a high-end wireless research lab like this, and it was incredibly impressive to see a MIMO system running at 130 gigahertz, and maybe more impressively with 10 gigahertz of bandwidth. Also in this lab, they figured out a way to split and bend sub-terahertz signals to effectively eavesdrop on RF communication beams, with interesting potential cybersecurity implications. So this is something that I don't normally see in this type of setup. We have one transmitter and two receivers instead of one transmitter, one receiver, which I'm used to. Can you talk me through what is this setup? What are we actually looking at here?
So this is a typical, it's not a typical, it's actually, it's a man-in-the-middle attack. So we call it a meta-surface in the middle attack. So the typical networking paradigm of man-in-the-middle attack, you have Alice trying to talk to Bob, and ideally it's an omnidirectional link, or it's a wired link. So if it's an omnidirectional wireless link, so if you are anywhere in the radiation pattern of that antenna, you can still eavesdrop, right? And then if we assume, of course, this is physical layer security, so there is no encryption, right? So if you can listen to the wireless signal, then you are eavesdropping on the link, and then you can hack the link, right? So with the terahertz communication link, this is 130 gigahertz, so it's sub terahertz, very close to the actual terahertz signals that frequencies that we actually want to reach to. So typically, what happens is that if so because of the terahertz channel, it's like you have very high propagation losses, right? So you have the pass loss, and you have a molecular atmospheric absorption as well. So what happens is that we use very directional antennas with high gain. So you have more or less a pencil beam size, right? A pencil spot. So this antenna gives you around 40 dBi of gain. So the half power beam width is around 1.6 degrees. So it's very, very narrow. So it's a more or less directional link. So how can you eavesdrop on a directional link without actually blocking the link, right? Because Alice is talking to Bob, and then Bob has to send an acknowledgement, right? So if you block the link, no acknowledgement comes back, and then the link stops. So you cannot successfully eavesdrop on the link. So what we designed with our collaborators at Rice University with Professor Edward Knightley is that these meta surfaces. So these are passive meta surfaces. They are very easy to manufacture. So you basically apply generalized Snell's law. So basic Snell's law tells you that if you have a mirror, you have an incident angle at the normal, then the reflection goes at the same angle from the normal. This is called specular reflection, right? So, but this is not a mirror, and this is actually a transmissive metasurface. So what happens is that we design very small meta-atoms across the whole plane, okay? So these meta-atoms, it has the shape of C-shaped split ring resonators. We designed that on console multiphysics, and then it's very similar to the process of etching. So you have a design, you print it on toner, and then you transfer that toner onto metal, or you metallize the toner, the pattern. And then this technique is called hot stamping. Okay. So we designed that on console with the different orientations. So you have here thousands of C-shapes. Each one introduces a phase response in a certain way, and then across that you introduce your phase gradient. So whatever phase gradient you can create, then you introduce, like you can actually do any arbitrary wavefront engineering. That's generalized Snell's law. So we have that, we print it, we metallize it, and then we put it on a piece of paper, a glossy paper like you see. So it's very cheap to manufacture and it's very light, right?
So we have this transmission beam and we're trying to snoop it. We're trying to do a man-in-the-middle attack.
To eavesdrop on the link.
Without them knowing that we're doing it.
Exactly.
Without ruining that communication.
So minimal effect on that party, which is the legitimate party, right?
Right.
So that it still sends the acknowledgement, everything is going well. Of course, you will introduce some attenuation, but it's very minimal.
So we have then our second receiver, which is trying to listen in, and by dropping in this hot stamped piece of paper with the open ring resonators.
Yes, the split C-ring resonators, you can basically put that here, and then you will start getting a signal.
And that's designed in such a way that it will basically split out part of the signal into this receiver.
It takes some power of the signal and then diverts it to that direction.
Okay.
And this receiver is a little bit rotated. It's rotated 90 degrees because this introduces cross polarization. So we designed that and we know how to eavesdrop using that link. We can just put this piece of paper here, and then you will start seeing something at the other channel.
So now that we've put the paper in place, the beam is being split and rotated, and we're seeing it on our main receiver, our
the legitimate
receiver, and our man-in-the-middle attack.
The eavesdropper. So if you block that, you'll find that your channel is blocked. If you block that, nothing comes here. And if you remove the metasurface, then you'll start getting only this one.
That is so cool.
So we are sending 5 gigahertz of bandwidth now. So 130 gigahertz RF, the IF signal, the modulated signal actually has 5 gigahertz of bandwidth. You can increase it, you can decrease it. Everything is very flexible because we design the discrete time waveforms in MATLAB, and then we use the arbitrary waveform generator from Keysight to actually, it's like a very high performance digital to analog converter, an interpolator. So whatever discrete time waveform we can design in MATLAB, do simulations, we can do it in real time. Using the Keysight AWG and the DSO, we get it back discretized again, and then we can get the discrete time waveform, process it in MATLAB, do these constellations. So we can now try to transmit. Yeah. So
that is so much better.
This is the constellation before. Equalization, then we use our minimum mean squared error equalizer, or we can try different equalizers, zero forcing according to what type of channel that you are expecting to have, and then we have this received. So of course we compress this so that we can send it fast enough. Yeah. And so this is a perfect constellation with 0-bit error rate. So we are not doing here any error correction or error control coding. So no redundant bits, no error correction, and you get 0-bit error rate at 130 gigahertz.
So no error correction with a 0% bit error rate.
Yes, no, without error correction.
Pretty exceptional.
Exactly.
That's amazing.
Our lab also, we designed different axicons and lenses that we can actually do different types of beams. So these are more or less Gaussian beams. So you can do Bessel beams, you can do orbital angular momentum. So you can also demonstrate with Bessel beams, if you have a stationary blocker, like in the near field, you can actually let this beam regenerate after the blocker. So you can do any type of wavefront engineering or wavefront manipulation. So if you have a small blocker in the near field, and then of course if you use a Gaussian beam, which is the ordinary beam, you will, if you're transmitting an image, then you will see this image like it has many errors, right? Because there is a blocker inside in the middle. But if you use Bessel beams, then it will regenerate and reconstruct, and then at the receiver you will get it. So you can do many cool things with these things. So yeah, the terahertz channel is a little bit difficult, so we said, okay, why not use directional antennas, right? But directional antennas introduced many other problems, right? But we have the solutions to these problems.
So once you solve the wireless and the phi layer problems, which is no small feat, you are immediately faced with a new problem. What do you do with all that data? It's more than just a layer 1 discussion. You have to build a network that can, in real time, process and handle the data. You need a network prototyping system, one you can quickly configure, test, and reconfigure and iterate, and it has to have blazing fast processing capabilities, something like this setup.
So we start off with theory. Now we're talking about next generation communication. We have an idea of what's the physical layer looking like, and that's because of the years we spent researching that using the offline kind of testbed that Keysight has, the DSOs, AWG, and the signal generators. When we were able to fully understand that channel at the 6G kind of domain, now we have a good idea of how to develop that physical layer. And now that we have that, we're developing a full kind of system on the hardware that consists of both a transmitter and receiver that operates in real time. And at the moment, we're just sending binaries, random data, but the goal is to be able to achieve that high sampling rate. And how do we achieve that? We're now looking at developing stuff in real-time hardware. So we need to consider resource utilization, clock speeds, memory capabilities. As well, we're processing a big chunk of bandwidth in real time. How do you process that without running out of memory and actually decoding that signal? And that's the solutions that we're coming up with as we go, and part of my research. And luckily, with the capabilities that Keysight is offering us with their hardwares, we can actually test it in real time and see if it actually performs as expected. And so far, it is. So we're looking forward to that kind of 6G capabilities that it can offer us. So when it comes to the sampling rate, it mainly consists of the data converters. It's very, very difficult to be able to set a data converter that can achieve that high sampling rate. And that's why for the longest time, we didn't have that capability. Everything was offline. You process that signal, you store it, and then you process it. So that's why a lot of the research has been stuck on physical layer. Now we want to move to the networking and higher end-to-end system. We need channel access kind of protocols, networking, transport. So that requires real time. And to get that real time, you need high sampling rate. So that's one piece of the puzzle. When we solve that in terms of the data converters and the analog domain of how they operate, now we need to, in the digital and software base, how do we process that signal? So we have a high sampling rate, but now we need to process it as fast as that sampling rate is. And that's another challenge. And one of the solutions that Keysight did was deploy high resource utilization FPGAs onto the whole prototype so that we can program those solutions on the FPGA that gives us access to those high processing techniques.
Okay. So prior to this, you would send a batch of data, you'd capture it all, and then you'd offload it and basically analyze it not in real time.
Correct.
But now with this FPGA system, you can do this in real time, and that gives you a lot more flexibility in terms of research and iteration speeds.
As of today, there's very limited research on the upper networking layers. We have amazing papers on physical layers, but very limited networking layer protocols. Why? Because all of our hardware was offline. We can simulate stuff, and that's amazing, but in the real world, when we want to push a protocol out, we need to test it in real hardware. We had no hardware until Keysight came up with this solution, right? So now we can actually test that and propose new networking solutions that can be in the forefront of those 6G standards. And with the capabilities that these hardwares gives us, we can actually demonstrate multiple nodes communicating in 6G, which has never been achieved yet. So we can start playing around with adding more nodes into the channel and see how they behave.
I never thought about having real-time hardware being a prerequisite for doing networking research. Blowing my mind a little bit.
Yeah, the reason behind that is we've been stuck with few chunks of bandwidth. So when you look at 5G, 4G and its predecessors, the bandwidth wasn't that crazy that we can still achieve that kind of sampling rate in the hardware that we had access to at the time. But when we look at 6G, we're looking at multi-gigahertz of bandwidth, and that's a very high bandwidth kind of capability. And you need to be able to sample it at twice that bandwidth. So if you're talking about 10 gigahertz of bandwidth, you need to be sampling it at twice that rate. So that's 20 gigasamples per second. We don't have that hardware at the time. Now we do, so now we can play around with that. So this is like 68 gigasamples per second, and that gives us around like 20 to 30 gigahertz of bandwidth that we can communicate on, and that's never been shown before. So in the sub-terahertz region, between 130 to 140, we have access to around 8 to 10 gigahertz of bandwidth, and that's contiguous bandwidth, so that's amazing. As you move up in frequency, like in the 1 terahertz, 2 terahertz, 3 terahertz, you start opening the door to multi-gigahertz of bandwidth. So you either can have them non-contiguous and you can just aggregate into multiple channels, or you can try to find somewhere in the terahertz band from 1 to 10 terahertz, somewhere where it gives you that bandwidth, which apparently there's an excess of it and a lot of it. I'm not the best in terms of frequency domain structure, because it also relies on the government and the FCC and how they dedicate those frequency bands to which specific uses. But the good thing about terahertz is it hasn't been utilized like its a lower frequency counterpart. So there's a lot of bandwidth, and we want to use that for communication, for high speed kind of applications. Maybe not for this generation, but the next generation, when we look at autonomous driving, AR, VR, edge computing, all that cool stuff that requires low latency and high speeds. And that's the next generation applications.
How much bandwidth are you looking at? Like what's a reasonable amount of bandwidth for your research?
So for now, and when it comes to research, we just want to show a high-speed ultra broadband, right? So we don't need to go crazy and go 20, 30, 40 gigahertz because we're not even ready yet to be able to understand and comprehend how big that is and be able to solve the problems there, right? So just 8 to 10 gigahertz of bandwidth is more than enough to be able to at least show some stuff working at that kind of scale of high bandwidths and some of the solutions from both physical layer all the way up to the transport networking layer. As of now, the system that I've been developing on the USB-A doesn't fully leverage that capabilities. We're starting slow and building our way up to maximize the performance and efficiency. So as of now, we're looking at around 10 gigahertz of bandwidth on the USB-A to be able to communicate in. And that should give us somewhere around a theoretical data rate or bit rate of 60 to 70 gigabits per second, which is still very, very high. But now when we push the limit to its capabilities, we're talking about somewhere near the 100 gigabits per second, which is very impressive. And I've never seen a wireless radio be able to communicate at that rate. So it's a very exciting time, and I'm looking forward to be able to see how we can push it to the limits and see what it can offer us. Think of it this way, like 10 years ago when you take a picture from your phone and the size of it is nothing comparable to the size it would be right now with your new high performance cameras, right? So things are getting bigger in size. So as we move forward with this like low latency, high speed, you want to push data really fast at a low latency, that's when things start coming into play in terms of terahertz. One cool approach that I easily come into mind is backhaul connectivity. For the longest time, we've been looking at fiber optics for your backhaul connectivity because it's most stable, high performance, and gives you the best speeds, right? But it's very expensive and infrastructure-wise, it's crazy. But when you start using this for backhaul kind of communication, it's wireless, software-based, easily deployable, especially in emergency situation. You just put it, plug it, and it works, and can offer you very high speeds that's comparable to fiber optics, right? So this becomes a very attractive solution for backhaul connectivity.
So instead of having to like lay fiber from one part of a town to another, you could drive 2 trucks up and point their antennas at each other and have a backhaul network on wheels.
100%.
That's
and
crazy.
Think about rural areas, developing cities, places where it's very hard to deploy that fiber optics in the first place. This becomes an amazing solution that can compete with fiber optics easily. Fiber optics will always be there. There's nothing that can compare with fiber optics. But if you can get really close to it and the situation like rural areas, it doesn't make sense to put fiber optics, why not use this? And that's when you start playing into the system of where to actually point this at.
I'm blown away seeing the diversity of research happening here. We have people working out and solving decades-old wireless physics problems, and then 10 feet away, we have someone else working on uncharted networking challenges. For a long time, this was all theoretically capable, but this lab is one of the first places that made it real. So let's circle back with Giuseppe to explore how these interdisciplinary research collaborations will help make 6G a reality.
All my work till 2017 was mostly equations and numbers, right? 2017, we got this support from the National Science Foundation to build the first version of the terahertz testbed, which we call it Terranova, and it was the first system at 1 terahertz. That was the big investment. That day, the day that money came, it was a huge learning curve, right? First of all my students were used to just do equations and numbers, right? Suddenly you say, no, here you have a $250,000 oscilloscope, don't break it, go learn how to use it, no? Or, work with the Virginia Diodes guys, and we have these up and down converters, so be careful with the static, be careful with all this, don't break anything, okay, right? So it was great, that learning curve. Since 2017, or I would say effectively 2018, of course, we continue to do our theory and numbers, right? Because theoretically, I can predict things. I can work on things that technology still doesn't support. But at the same time, I want to back up as many things as possible. So the way we conceive an idea is like, okay, what can I theoretically do? Write the equations, do it all, and then let's see how much we can validate, right? If we look only at what we can validate today, then we are probably cutting ourselves short. Because sure, I'm ahead today, but I may not be ahead in 2 years or 3 years or 5. If I don't look at the experimentation, it means that my work lives in its own realm and no one cares. So it's finding that trade-off also.
When you got that funding, what went through your mind, and how did you start partnering with Keysight? Because this is quite the setup.
If I can be fully honest, so pretty much what happened is like, okay, well, I'm not an experimentalist. I have to become one. So we started looking, and honestly, I started looking at specifications, right? So my main driver is I knew that some companies like Virginia Diodes could help me get up to the right frequency, but I needed a starting point for the carrier frequency. So I needed a very stable very low phase noise oscillator, and of course then came across to your PSGs. Then I remember, I don't go to terahertz just to then make a 20 megahertz signal. I go to terahertz to make a 20 gigahertz signal at least, right? Then we start looking at arbitrary waveform generators, and we came across your M8196 platform. Said, okay, this is actually, top notch. Then we realized, well, that's the transmitter. What happens with the receiver? So we start looking at the oscilloscopes, and again, we needed someone able to sample very fast. So digital storage oscilloscope. We ended up with one of your Z series at that time. At that time was the best you could get, 63 gigahertz of bandwidth, which means that with that oscilloscope, sure, to do terahertz, you need up and down converters, but if you're just working at millimeter wave frequencies, you can connect an antenna there, and you see in real time your 5G signals.
Yeah.
I mean, that's, sometimes I work with, Tomas or Dimitrios, others in the institute, say, sure, we can down convert it if you want to baseband, but just put your 5G antenna there, and I can see your frames going on over the air. That's impressive.
Awesome. Yeah.
And then what happens? What I like from Keysight, and I'm not saying that just because you're Keysight, but what I like is that, first of all, I was always able to ask technical questions and get a technical answer. I even at that time, the person who was helping me, I was Buffalo based, I even asked him, so I'm trying to compare these two models, and he sent me a whole presentation about the good and bad, right? Yep. That helps a lot. Then, of course, we start moving, and I always say the same, when things work in the way I work, look, everyone has limited time in the day. So at the end of the day, I only have, you can spend your whole time complaining. There are people who live online just trolling and complaining. I prefer to live my time with the good things. And when I find something that works, I make sure everyone knows, right? So when I go around and present my testbed, there is your logo, there's VDI logos, and to some extent you can think of me as a working commercial, but no, I mean,
we'll take it. Yeah.
I just do what I think, if something works, why not to have more people, right? And that's how we got into Keysight. Then once you are in an ecosystem, it works. And what I really like from Keysight is that at some point, I usually say that when I talk with anyone at Keysight, I don't feel like a customer-seller relation. I feel like a collaborative relation, right? And look, the USB platform is something that we're working with you to build, and it's very exciting. At the same time, it's a huge responsibility. If I mess up in an NSF project, it's okay, Nothing critical happened. If I messed up in one of your products, right, then maybe Roger will not be too happy.
Well, speaking of Roger Nichols, Keysight's 6G program manager, he's here with me today so we can keep digging into 6G. If you have questions, those of you who are watching, click the chat button and put your questions in chat, and we have experts there answering those for you as well. But first off, Roger, thanks for being here.
It's a pleasure. Thanks for having me.
It seems like 6G is not fully developed. There's still a lot of room for innovation.
Plenty of room. There's a lot going on.
So moving up into higher frequencies, as we just saw at Northeastern, sub-terahertz bands are difficult. The physics is hard. There's a lot of networking stuff that's going on. Why do we even want to consider going up to above 100 gigahertz for communications?
The very high frequencies have the benefit of having access to a wider bandwidth. And you and I use a lot of data on our mobile devices. It's all about more data or more capacity. So first and foremost, going up to above 100 gigahertz could buy you very high bandwidths, as you saw in the demonstrations, and super high data rates. But also, one of the benefits is the highly directional transmission, the radio transmission, which is out of necessity. Also, as you saw in one of the other demonstrations, allows for a higher degree of security because it's much harder to eavesdrop something that is transmitted in a specific direction. So that's all part of what's going on, but it is a challenge. The semiconductors are expensive and exotic. The antennas are difficult to manage. Mobility is very difficult to manage, pointing the beam in the right direction. And so that ends up being a significant issue. But that's why everyone is doing the research, which is how do we solve these intense problems.
It's an interesting shift and challenge from today and the last 10 or 20 years. We've been trying to squeeze more and more into a very narrow band. But then when we look higher up, we get these really wide bands, but then the physics and all the other stuff becomes really challenging.
Yes, and the big challenge, and this is part of what's happening in the industry now, is that the frequency range 2, the millimeter wave spectrum, 24 to say 52 or maybe up to 71 gigahertz, has not been successful from a business perspective for the mobile operators. And a lot of that is because there's no killer app that is driving the volume that would drive down the costs and the economy of scale. And so the industry is a little bit skeptical about moving to even higher frequencies in this space. And so are we going to see sub-terahertz capability as a mainstream in 6G? I don't think so. Because it is many challenges to overcome. There's a lot of work that still needs to be done at lower frequencies. But the research is happening all over the place. We see plenty of activity there. And we also see some early niche applications of sub-terahertz or greater than 100 gigahertz frequencies in very high bandwidth point-to-point communication, some of which have been commercially demonstrated or publicly demonstrated within the last couple of months.
Can you give a couple examples of when that high bandwidth point-to-point communication might be useful?
Well, the backhaul capacity issue is a significant challenge for mobile operators. And since you cannot bring fiber to every base station, what happens is backhaul ends up being aggregated. So multiple base stations, the backhaul and the data that is served by those becomes aggregated into single connections. And if you can't bring fiber into a particular location, which is very expensive, laying fiber in the United States is about $100 a foot.
Goodness.
So when you aggregate all of this backhaul, you might not have the luxury of laying that fiber where you need it to. And so as the backhaul gets aggregated, the data capacity demand goes way up because you've got multiple base stations at the same time in both directions, downlink and uplink. And so one way to overcome that is with a radio link, and even now the radio links are becoming congested that are typically used for backhaul. So these very high frequencies with the super wide bandwidths available to them can help overcome those kinds of problems in particular cases.
That seems super useful, but I also feel like we're going back to the days when I'd like go to my grandparents' house and try to watch satellite TV on a rainy day, and it just wouldn't work. Are we gonna like lose internet when it rains?
Well, so the physics of the transmission are a reality. Snow and rain do cause problems. I have some of those stories myself, but we fortunately are not communicating a few hundred kilometers to a few thousand kilometers
Sure.
for these point-to-point links. They're much shorter. Some of what's going on in this research is to decide how do we overcome some of the issues with respect to change in propagation loss based on the weather.
You mentioned security briefly, and at the Northeastern lab, we saw that really interesting attack with the resonators that were splitting the beam off. How much is security a concern for 6G? New vulnerabilities, new attack vectors? Can you kind of lay out the landscape for me?
Yeah, so cybersecurity is a big deal for everybody. We've all had experiences, both good and bad, in that space. Every generation is designed to improve how secure it is over the last generation.
Okay.
And so 6G will have security features that 5G does not. 5G definitely had security features that 4G did not. But there are more things that we have to worry about. First of all, we have new technology in 6G. So every time you implement something new, whether that's you develop a new standard or how you implement the standard, you run the risk of introducing vulnerabilities that you don't realize until they're discovered later on. And in that situation, there are vulnerabilities in even 5G that are being discovered today and resolved, right? That's great. But we have the opportunity to introduce more, and that's a challenge. That's issue number one. Second thing is innovation is not exclusive to the good guys, unfortunately. In fact, the innovation that I've seen that some of the cyber crooks have thought up is fascinating, and in a morbid sense, it's respectable. It's amazing what they've come up with. So what's secure today is not secure tomorrow. And so there's constant work, and this isn't exclusive to 6G, but there's constant work to keep on top of what the other side has thought of and how to overcome those. And some of those are very complicated and very technical, and sometimes it's very brute force. The third issue is that the whole point of moving to the 6th generation, a little bit like what we did with the fifth generation, is to add capabilities to the network to greatly expand how it is being used. So not just for communications or social media, but as a fundamental part of societal use. Mobile banking, healthcare, you could imagine, and driving, navigation, all kinds of things. Well, when you expand how it's being used, you expand what we call the threat surface. And there's a lot more ways to take advantage of a vulnerability if something is used in a lot wider variety of manner, right?
Sure.
And so that is all of what has to be considered. And all of that is getting a tremendous amount of work. Even now, you can see in 3GPP, in the SA group, they're very focused on putting together, what is it going to take? What is going to be the security requirements for the 6th generation? And with what has now become a lot going on related to zero trust, which is a relatively new paradigm, I guess, in terms of cybersecurity. A lot of that is being built in as a fundamental assumption in terms of how 6G will be designed, is to enable a better implementation of a zero trust approach.
One of the other things that was interesting about 6G, and we see it with 5G and 4G, is disaster management. There's wildfires going on, or a hurricane blows through and someone will roll up and set up their own mobile network. Is there a world where 6G can also play that part, or are we going to stick with a more traditional 4G, 5G network?
So I think there's fundamentals like mobile base stations or cell on wheels, a cow, as they call them in the industry. And those come in multiple formats, even self-contained trucks that are one or multiple cell sites that can drive to a particular location, set up. They have microwave backhaul built in. They're pretty cool. I've seen these demonstrated, and that kind of thing for emergency coverage or potentially other areas, that's all been around for a while. And will those have 6G technology implemented on them? Absolutely. But what's happening now is a couple other technical, I suppose, innovations. One of those is the idea of a mobile base station, which is being worked on now in the specifications body in 3GPP. And you can imagine the added complexity of having a base station that can move around. But what will that buy you? If you put a mobile base station on a UAV, you can move it over to a place where it's needed for coverage for emergency situation or maybe other issues like precision agriculture or others. And that would greatly enable having the communication where you need it and even having it move, because disasters are not always stationary. So that's a huge benefit. And then the other thing which you see on the news all the time now is the integration of terrestrial cellular with non-terrestrial networks. And non-terrestrial can be, as I started with, a UAV, it could be a high altitude platform, or I believe what they call a HIBS, H-I-B-S. And the last thing is a base station. So it's basically an elevated base station somewhere high, either tens of meters or thousands of meters up, or even in the satellite area, all the way up to geosynchronous or geostationary. So either one of those could be used, and then you end up with the coverage you need because it augments what's in the terrestrial network. And so that's starting now with 5G. Even release 17 had NTN, non-terrestrial network specifications built into it. But you will see that continue to advance. And as 6G is developed, it will be developed with the fundamental assumption that integration with non-terrestrial networks is just part of how 6G is going to be put together. So that will be better for taking advantage of a satellite infrastructure that's already there.
Sure.
For the sake of this kind of application, among many others. And so to me, it's not exclusively a 6G thing in terms of disaster management and coverage where you don't have it. But as 6G evolves, it will become a much more pronounced way to manage those kinds of communications. I'm pretty excited about that as well.
So when it comes to setting up a 6G test system or a test bed, what does it take? Is there a one-size-fits-all solution, or what are the different considerations?
Well, a test bed is a big generic term. And so it really depends on what you're testing, what your research is. And so Josep demonstrated what he calls a test bed, what we call a test bed, but that's really exclusive to sub-terahertz radio communication system, right? A transceiver system and all of what you have to manage in that space. There are test beds that we've helped people develop that don't have anything to do with radio. It's all exclusive to what happens in the network, whether that's managing traffic patterns or how to allocate network resources and that kind of thing. So it really depends on what is being researched and what people want to test. Keysight is involved now in leading a project in Europe. It's called the 6G Sandbox, and it is a big test bed for 6G, and it is physically located in Spain with remote capability that other entities can use. And that test bed does more than just radio. It does radio, it helps folks understand how to apply edge computing capability. There's open RAN management capabilities, all kinds of things there. So it really depends on what folks are studying. Is it AI? Is it network capability? Is it radio? And what I encourage folks to do is think about what that research is and then recognize that, one of the neat things about what we do is we have a huge variety of capability across all layers of the protocol stack and from research all the way through deployment and even demise. And so a number of tools, software and hardware, that can be applied, particularly in an experimental situation, and also some design and simulation software, those kinds of things.
So it really depends on what you're trying to implement or research, and that will influence whether you're doing like network stuff or radio stuff. It's all kind of bespoke. So really, ultimately, give us a call.
That's how it works. And we're excited to be part of that, because part of this is we learn a lot when we see how people use the test and the design and the digital twin capabilities that we have. It's super informative, and it's, we're all technical, so we enjoy these kinds of things just to learn about what goes on there. But that's the conversation that I encourage everyone to initiate.
Wonderful. How is AI useful for 6G, if at all?
Well, from the very beginning of the 6G work that was done, that I could see stretching back even to 2017, the fundamental assumption is that AI will be used in 6G from the very beginning. Whereas it's built onto 5G or being built onto 5G, 6G will be designed with the assumption that AI, and particularly machine learning, will be part of the system. Well, what does that mean? Most of what's in the news for artificial intelligence now is related to large language models or image or video recognition or deep fakes or things like that, right? So those are all a particular set of data and models. But for 6G, while large language models will be part of how people use the system, to make the system work better is a different set of models. And it's really, I guess the way I like to see it is using AI to overcome the complexities in the systems that we design and to simplify those, or to overcome some of the demands from the laws of physics. And so this has to do with everything from enabling circuit design to improving the knowledge that the radio has of the radio channel state so it can make real-time adjustments, to improving how we manage traffic flow over the air, deciding how you're going to allocate radio resources in the base station, deciding how we're going to manage traffic flow in the network itself once it gets into the wired network, deciding how compute capability will be distributed between the edge and what happens in the cloud. All those kinds of things will be, actually are being researched. Can we use AI to make these better than they were in legacy systems? Some of that research is going to come up with some brilliant stuff to make things easier to manage, because machine learning lends itself to complicated environments where the statistics will prove things out. In some cases, they're going to fall on their face, and we'll learn that, okay, we're not ready for that yet. So will 6G require AI, or will AI make 6G better? The answer is yes. Not necessarily how everybody thinks, but by all means, it is a fundamental piece of research that's going on throughout the industry. We're doing it ourselves, and we're working on a number of ways to help our customers enable AI, managing data, figuring out how to do validation of AI-enabled systems. Even the AI development process is a key issue because it's new to a lot of the folks in the industry. So by all means, the short answer is yes.
Okay. When you look at the future of where 6G is going, and maybe we're in a, I'm not going to say final state of 6G, because just like 5G, it's always going to be evolving. But when we're in a, I'm going to call it like a mature deployed version of 6G, what about that infrastructure or that world that we will live in gets you most excited?
I think, to me, the most exciting part of that vision is how the wireless communication will move into being a fundamental part of our society. It kind of is, we kind of think about it a lot, but still most of what we use mobile phones for is entertainment and advertising. And so that's great. It makes us all a lot of money, but
some people.
But the point is that what that can do for healthcare, what that can do for education, what it can do for the basics of running a government are significant. And once the system is flexible, cost-effective, energy efficient, and secure enough to enable applications that we would not have otherwise considered for mobile communications. To me, that's the exciting part of where this is going to go. And obviously, we're technologists, so all the tech that goes into that is a lot of fun to work on. And that part is great, but the exciting part for me is that expansion of the application space and really taking full advantage of this wonderful wireless communication technology that started more than 100 years ago.
Yeah. Sometimes there's a joke that Simpsons did it, but sometimes in tech it feels like Star Trek did it a little bit because, the communications and the medical wireless it feels like there's so much vision set up and so much good for humanity and the quality of life for people everywhere that we're potentially unlocking here with 6G.
I think that's the intent, right?
Yeah.
And there's obviously going to be all the traditional business models around this,
Sure.
but I think the expansion of this technology is what is exciting to me. And the economy of scale that you get with a global implementation of, a single standard is what will make that truly effective.
Wonderful. So that is all the time we have for today, but Roger, thank you for being here.
Oh, it's a pleasure. Good to be here. Thank you.
And thank you all for tuning in. I hope it was helpful. Check out the link below if you'd like to start a conversation with us. And I'm Daniel Bogdanoff, joined by Roger Nichols, and we'll see you next time.